All right, diving into reaction number 3 here with hydrohalogenation of an alkyne. When we look at hydrohalogenation of an alkyne, it's very similar to our hydrohalogenation of the alkenes we saw in chapter 8. The only big difference here is that we can do one equivalent of HX, which will react one of the pi bonds. We can also do excess of HX, and we can make geminal dihalides, where the halogens are on the same carbons. So these geminal dihalides are important for us to be able to make so that we can think about having multiple functional groups, multiple leaving groups. So let's go ahead and see how we make these. One equivalent at a time. You can say excess and you go straight to the gem dihalide, or you can do one equivalent at a time and have that intermediate that we see here. With HX, again, this was our proton transfer first step. And so if we imagine carbon 1 and carbon 2 of the alkyne, the pi bond breaks, adds hydrogen to the less substituted carbon, and it adds a carbocation to the more substituted carbon. Now, with this mechanism, this happens, the second step happens extremely fast, where we get the halogen ion to come right back and add onto that carbocation. The reason for that is this is a vinylic carbocation, very, very high in energy. We'll look at the transition state in just a second to see that in reality, we actually believe that these two reactions, the proton transfer and the nuke attack, happen at the exact same time. Why we think that is because of kinetics. We see that 2 equivalents of HX is needed for every first step in this reaction. And so thinking about that kinetics, the vinylic carbocation as well is extremely high in energy. And so we do not see any carbocation rearrangements here. We believe that this reaction happens very rapidly. Our second equivalent of HX will happen just like before in chapter 8. We do have a carbocation here, but again, it will not rearrange. And the reason why it won't rearrange is because it is resonance stabilized. That halogen that was added first is able to provide resonance stability to that carbocation. Draw that resonance structure right down here. So we do know that that is the most stable carbocation that we have. Moving forward into the actual nucleophilic attack to make our geminal dihalide, we see the halogen ion can come back and attack that carbocation. This is the transition state that we believe happens for that first equivalent of HX being added across the alkyne when one pi bond reacts to pick up the proton and do that first proton transfer. It is believed that the second equivalent of X is already starting to come in. And so this is a transition state that is believed why the first equivalent of HX being added across the alkyne happens very rapidly. Hydration reactions we saw before, we have adding water across that double bond. We do see something slightly different here, and this acid catalyzed hydration has an extra reagent, namely that is mercury sulfate. And so mercury sulfate is actually used to stabilize and to create a more stable intermediate. Again, the vinylic carbocation is probably not likely. And so we're going to walk through this mechanism, also noting a couple of things with the regioselectivity here. Oxygen is going to be added to the more substituted carbon. However, notice we don't have 2 alcohols here. Acid catalyzed hydration in this mechanism of an alkyne results in a ketone. We're going to see what happens with that and the intermediate that forms to produce this ketone as a product instead of an alcohol like we saw in chapter 8. All right, so for this curved arrow mechanism, we're going to start with the actual mercury sulfate. Mercury sulfate is going to be a mercury +2 cation. Sulfate is the -2. Mercury there in that formula unit is a +2. Pi bond breaks, attacks the mercury. Back bonding does occur, just like we saw in oxymercuration before. And so we make this bridged mercury ion again. And this is what is helping stabilize any vanillic carbocation that we can think of. We believe this is the mechanism that occurs instead of a carbocation. Again, no carbocation rearrangements here. Water, just like before in a bridge, will attack the more substituted position. So we'll have a mercury +1 cation now, it gained that electron, and we have water added to that more substituted position. We'll do a deprotonation step to make that a neutral alcohol. And from here, it's a kind of a cleanup step to get rid of that mercury. In that proton transfer we just did, we made hydronium. And this hydronium is what's going to be able to help us get rid of the mercury and clean up our molecule. The pi bond breaks, the second pi bond breaks, adding that extra proton. The more substituted and more stable carbocation is going to be the one next to the alcohol. Why? Because of resonance. And that's what we see in this next step. Resonance occurs to form a double bond between the oxygen and the carbon. And then finally, mercury will leave as the +2 cation it started with. And we form an intermediate that's an alkene and an alcohol. This intermediate is called an enol. Alkene plus alcohol, so enol. Now these enols undergo a rearrangement of their atoms. It forms a constitutional isomer that is called a ketone. Why? If we think about this rearrangement, it is an equilibrium. Notice what happened here. That one pi bond that's left over switches locations. Instead of a carbon-carbon double bond, we have a carbon-oxygen double bond. That extra proton actually goes to be placed on the end carbon and was a CH2, and it becomes a CH3. This ketone is a more stable final product. These are called tautomers. They are constitutional isomers that are linked together in an equilibrium reaction. And the process of switching from the enol to the ketone is called tautomerization. Now, because we are in an acid catalyzed hydration, we will be undergoing the tautomerization via an acid catalyzed reaction. Let's go ahead and look at that reaction. First thing that happens is in our enol, we have the pi bond breaking to pick up the proton in H3O+. Again, the carbocation goes on the more substituted position, the one with resonance from the oxygen alcohol. That oxygen can actually undergo that resonance structure to where we see the carbon-oxygen double bond, and then we simply have a protonated ketone. That protonated ketone then can be deprotonated by water to make the final ketone product. So again, when looking at these carbons 1 and 2 that had the triple bond, we see there is a regioselectivity to put the oxygen on the more substituted position and keep it on that more substituted position. Instead of adding a second alcohol, instead of adding a second water, that carbocation undergoes resonance. Resonance is a lot faster than any intermolecular reaction. Now, just like we saw before as well, we have the anti-Markovnikov, the regioselectivity to put an oxygen on the less substituted center. If we count these carbons 1 and 2, we see that carbon number 1, the less substituted carbon, had the actual oxygen. And so thinking about this reaction, the only difference between our hydroboration oxidation reagents from chapter 8, the alkene chapter, to now chapter 9, the alkyne chapter, is we have a much larger boron reagent. Normally, we use 9-BBN. We can also use dicyamyl borane. Let's just draw a couple of these structures. It's not necessary that you draw these structures yourself, but what I want to think about is how the size of the boron molecule has changed from chapter 9 and 8. There's dicyamyl borane. 9-BBN is a eight-membered ring that has a bridge in it, so it's a bridged bicyclic ring. And that bridged bicyclic ring has the boron to the hydrogen on it. Again, you don't need to draw these, but it is going to be important to note that these boron reagents are a lot larger. And the reason for that is so that we get the aldehyde product. I'm going to use R groups and an H there to be able to emphasize this mechanism. Again, the first concerted step is the exact same as what we saw before. I'll just spread this guy out a little bit. So the pi bond attacks the boron. The hydrogen comes back and attacks on the less substituted side. So we do have a syn addition. And then the oxidation step, we do not need to know the mechanism for. That simply changes to our enol. And just the same way, again, what we saw with our enol from acid catalyzed hydration, our enol in hydroboration oxidation also can undergo tautomerization to the keto form. But again, this specific keto is going to be an aldehyde. So again, these are tautomers. Tautomerization will favor the carbon-oxygen double bond, just like it did before. Just now, remember in step number 2, we are in sodium hydroxide, so we are base catalyzed. Let's go ahead and look at that tautomerization. Here we see that proton transfer is also occurring, just this time, it's the proton of the alcohol that is being pulled off. Again, we see resonance stabilizing that enolate ion intermediate. So oxygen can roll its lone pairs down and can pop a lone pair onto a carbon. That's adjacent. And then that carbon, again, base catalyzed, will pick up a proton from water and make the actual aldehyde final product. So 2 different tautomerization reactions. But again, converting an enol to a carbon-oxygen double bond final product. All right, halogenation, no mechanism for this one. What we see is the only reaction that is extremely helpful here is when we add excess Cl2 or Br2 across that triple bond. Now, okay, we have a triple bond, so 2 pi bonds. We are going to be adding 4 sigma bonds, and those 4 sigma bonds will all be to the same halogen. So looking at this reaction, no mechanism, CCl4 is the reagent. It's to make sure we're not adding water, and it's just to make sure that we have enough of our movement of these reagents to be able to make that final tetra substituted alkyl halide product. if you did one equivalent, why we don't really like to do this reaction, you'd think because of halogenation of the alkenes, anti-addition would be the only product, but we actually see that this mechanism is not well understood because we do get not only the anti-addition, but we also get the syn addition. This is one really good example of how organic chemists kind of know what's going on, but not really. And so finding out what this mechanism is high on the priority of some people. No mechanism because we really have no idea how it happens. How do you get syn addition with halogenation? Well, it's something different than what we saw in chapter 8. What that difference is, we don't know yet. The last one that we want to talk about is ozonolysis. Again, no mechanism for this one. This is going to be very similar to what we saw in the last chapter. Ozonolysis here, the only difference in the reagents is we can just simply use water for that second step. And ozonolysis breaks apart all of the sigma and the 2 pi's to create fully oxidized final products. So I'm going to count here across the entire molecule so we can see what happens. Carbon number 1 and 2 get separated. 3, 4, and 5 are on the other side. Carbon number 2 and 3, part of the alkyne, get fully oxidized, which means we make carboxylic acids. Now, that would be an internal alkyne. The only difference for a terminal alkyne, the one at the end, is what happens to that final end carbon. So we'll count again, 1, 2, 3. With ozonolysis of a terminal alkyne, we again split everything apart. Carbon number 2 will make the carboxylic acid. Carbon number 1, because it's terminal, gets fully oxidized and it becomes carbon dioxide. This is carbon number 1. I just wanted to make that atom count a little bit smaller, and it does bubble out of solution. So terminal alkynes can undergo ozonolysis to make carboxylic acids and carbon dioxide. So carbon number 1 being at the end there gets fully oxidized, as much oxygen bonds as you can imagine, which would be carbon dioxide. All right, alkylation is not an addition reaction. It's our last reaction in this chapter that's not adding to the pi bonds. The pi bonds are actually going to be staying put. The only thing that we are going to be doing is a first acid-base reaction. What we see is a strong reactive base, one that can deprotonate that terminal alkyne. Remember that terminal alkyne has a pKa of 25. And so it's that hydrogen that we are going to be replacing with a methyl group in this second step. So the first step is going to be a proton transfer. The second step is going to be an SN2 reaction. Everything that we learned back in chapter 2. All we're doing in this first step is actually making the alkyne a more reactive nucleophile. Alkynes are really good at being deprotonated as long as you have the right base. So the amide ion is a favorite. You can use hydride. You can also use LDA. We'll see that a little bit. Any of those nitrogen negative charged bases or hydrogen negatively charged bases. Proton transfer. Take that terminal alkyne and make it an ion. So now this is a new nuke. Small enough, there's not a lot of steric hindrance because remember of this linear nature right here. And so that's what makes it a really, really great nucleophile to then go ahead and attack and then write out our CH3Br so that we can see alpha carbons getting nucleophilic attack with the loss of the leaving group. This has to be an SN2 reaction. This is a reactive nuke. and a less substituted alpha, right? It's a methyl halide. And so we'll get that extra carbon added on. How cool is that? Adding carbons to our organic molecules, super fun. Just as a reminder, SN2 reactions can be performed by methyl halides, primary halides. They can be performed by secondary alkyl halides as well, but methyl and primaries are the best. All right, looking at all the reactions that we have, take a minute to go through these and to see which ones are addition and which ones are just reacting with that alkyne, because we have a couple of different things that we can do with that alkyne now, such as alkylation, adding R groups, adding extra carbons, ozonolysis, which oxidizes our alkyne, and then we have a variety of addition reactions. We're going to practice synthesis again when we meet together. So it would be really, really important to make sure that you understand each of these forward reactions and all of their reagents and the functional groups of those products before doing that synthesis. Thank you very much.